This is the study session on fixed income and the reading on understanding fixed income risk and return. I believe we had a reading back under equity analysis that was called something similar, understanding equity risk and return. And so we're going to apply a lot of the same principles, but our terminology is going to be very, very different. So even though there are a couple of command words in the LOSs that sound like compute and calculate, and we're going to have to use our calculators, of course, there are enough describe and compare, so we're going to have to make sure we understand this new terminology. All right, let's go ahead and calculate and interpret the sources of return from investing in a fixed rate bond. All right, let's just remind ourselves about fixed rate bonds. What are we doing here? We're either a government or a business, and we're issuing a bond. We're issuing a bond because we have something to do with that capital. If we're a corporation, it's probably invest in a positive net present value project. If it's the government, it's to provide some kind of services. All right, but either one of those makes an explicit promise to the bondholder. The borrower says, I promise to pay you interest and I promise to pay you principal. So there are three possible sources of returns. All right, there's that receipt of the promised coupon and the principal payment. But on top of that, what we're going to do is we're going to reinvest those coupon payments. And the future value of those reinvested coupons, of course, depends on the reinvestment rate. And I have a good example to show you here in the next slide. And then, of course, if we hold the bond until it matures, we'll get the $1,000 principal payment. But if we sell it early, we'll have either a capital gain or a capital loss. And that sums to the total return on a fixed rate bond. Now what I want to do is I want to take a little bit of a sidetrack here just for a minute to show you some really, really important math so you can understand the concepts that we're going to talk about for the rest of the slide. Now back here, we said that one of these sources is to reinvest the coupon payments. All right, so let's suppose that as the bondholder, we receive all of those coupon payments and we reinvest them. And then at the maturity date, we get that $1,000 back. We want to know what that future value is. We're going to call that the terminal value of the bond. All right, so let's consider a simple bond, a simple option-free annual pay bond that has a coupon rate of 5%, yield to maturity of 5%, and a maturity date of 7 years. All right, so this bond is going to sell for $1,000 today. But what will you get if you're the bondholder? You're going to receive 7 $50 coupon payments and then one $1,000 principal payment. Terminal value then depends on the ability to reinvest the coupons. All right, so let's go ahead and do the math here of this one. Suppose the reinvestment rate is 5%. So the yield, the coupon was 5. Let's just suppose that we can reinvest at 5% over the next 7 years. At the end of 7 years, the bondholder will have $1,407. All right, let me show you how to calculate that. Go ahead and get your financial calculators out. We make payment 50. We make N 7. We make present value 0. We make I, which is the yield to maturity of 5. Solve for future value. So our future value of the reinvested coupons is $407.10. Add that final $1,000 principal payment and you get the $1,407. All right. Now, I don't show you the math here in this slide, but if we can reinvest at a lower rate, let's say 3%, terminal value is just $1,383. And if we can reinvest at a higher rate, let's pick 7%, then terminal value is $1,432. So note that at the end of 7 years, the bondholder really doesn't know what he or she is going to have in terms of a terminal value. It depends entirely on that reinvestment rate. All right, this is called a big part of interest rate risk, the uncertainty over terminal values. And remember that lots of investors, lots of bondholders, they invest in these fixed income securities because they want to finance a future purchase, Whether that future purchase is build a swimming pool in the backyard or buy a beach house or fund children's college education. This is interest rate risk. All right, so the question then becomes, how do we manage that interest rate risk? We don't want to buy a bond and hope that we have in this example, let's say we hope we're going to have $1,400 at the end of 7 years, but because interest rates fall and they're only 1 or 2%, maybe we only have $1,100 or $1,200. And then we have to skimp on whatever it is that we were going to buy in 7 years. All right, hold off on that thought. Let's go to the next slide. Notice that in that example, the investment horizon was exactly equal to the maturity date of the bond. We call that interest rate risk. But what if our investment horizon is just 6 years? So we're going to buy a 7-year bond to finance a purchase in 6 years. Now let's go ahead and recompute terminal values, but note that the bondholder will have to sell the bond 1 year before it matures. All right, so let's work through the math here. Let's suppose the reinvestment rate is 5%. The terminal value will be $1,340.09. How did we get that? Same way we did before. Let's calculate the future value of the coupon. So payment is 50, N is just 6 now. Present value is 0, I is 5. All that's the same. Those other variables are the same, except for the N equals 6, as in the previous example. And let's solve for future value. We get $340.09. And then we're going to sell the bond. But note that the coupon rate and the yield to maturity are still 5%. So the future value of the bond is going to be $1,000. I show you the calculations there just so you can verify that. All right, you got this? So terminal value at 5% after 6 years is going to be $1,340. Now, remember, today we don't know what that reinvestment rate is going to be. So let's suppose that rates either go up or down. So in the second example, let's suppose that the reinvestment rate is now 3%. We go through that same kind of a process. The terminal value is going to equal $1,342. If the reinvestment rate is 7%, if we can reinvest at a higher rate, terminal value equals $1,338. Oh my gosh, do you see what's going on here? The terminal values are almost identical. Go back to our previous example. There's no way those were identical. 1407, 1383, 1432. Let's suppose that you bought 10 of these bonds and you wanted to build a swimming pool at the end of year 7. So notice at the end of year 7, you could build a swimming pool for either, well, move the decimal over. What's that? $14,071 or $13,830 or 14. So there's a big difference. So at the end of 7 years, you might be able to build a bigger pool, or you may be able to build a smaller pool. That's called interest rate risk. But look at this. If we lowered our investment horizon to 6 years, we're going to essentially have the same terminal value. We're not going to care whether interest rates go up or interest rates going to go down because we're going to have our 1340. So terminal values in this case are essentially identical, and this means that interest rate risk has essentially been eliminated. Now, the reason that this works is not because I just picked 6 years randomly at the top. It's because of some important risk concept in the fixed income world. The reason this works is because we match the investment horizon. We're going to build the swimming pool in 6 years with not the maturity date of the bond, but something that's called the duration of the bond. Now, I'm going to define and explain and calculate duration here in just the next couple of slides, but I want you to get this in your heads right now. Duration is a measure of interest rate risk, and duration for a fixed income security is similar to the beta for an equity security. Remember how important beta was? Oh my gosh, the measure of systematic risk. That was extremely important. Well, duration holds the same status in the fixed income world. Now, let me just pause and give you one follow-up here. The duration of this bond that I picked was actually about 6.1 years, which accounts for the slight difference in the 1340 and the 1342 and the 1338. If we found a bond that had exactly 6 years of duration, then those would all be 1340 or 1342. This is really, really cool stuff. All right, so let's go ahead and define and calculate and interpret all of these different kinds of durations, which is really the focus of this reading. All right, so notice what I said to you. Duration is a measure of interest rate risk. So here's the definition in the reading. It measures the sensitivity of the bond's full price, and we did full price in the previous reading, to changes in the yield to maturity on the bond, or in a general sense, changes in the benchmark interest rates. All right, so what do we know? We know that if we own the bonds, we know that when yields go up, this is bad news because the price of all of our bonds are going to fall. But the question then becomes the following. Will all of our bonds fall by the same amount? And the answer is of course not. Some bonds are going to overreact. Some bonds are going to underreact to that changes in yield to maturity, and it depends entirely on the duration of the bond. Now, the simplest of all durations is called Macaulay duration. And this is really just a weighted average time to maturity. So the maturity date in our previous bond was 7 years. And the Macaulay duration, let's just suppose that 6.1 was the Macaulay duration. That's the weighted average time to maturity. And this is really an important concept. I want you to think of it in the following way. It's the weighted average time until you're going to get all your money back. So let's go ahead and just review a second. When we had this 7-year investment horizon, we knew we were going to get all of our money back in year 7. But in year 7, we didn't know what we were going to get. We didn't know if we were going to get 1407 or 1383 or some other number. Because look, I only picked 3 possible yields, reinvestment rates. Yields could be 2% or 8% or 25%. But what did we do here? When we had the duration of 6 years, our terminal value was almost identical, virtually identical. All right, so that's a really important concept. It's a weighted average until you're going to get what you think you want to get out of it. What was that number back there? 1340. Now, there's a good formula for you guys to memorize. And boy, it would be tough if you were asked to, and look at the LOS. It does say calculate. If you were asked to calculate the Macaulay duration for a 75-year bond, I mean, just think about it. You'd have cash flow 1 times 1, cash flow 2 times 2, cash flow 8 times 8, cash flow 33 times 33. So you'd be here all day. And so really, from an academic standpoint, you probably are only going to have to do this for a relatively short bond, a bond that has a short maturity. So here's a quick example. Suppose we have 3 years to maturity, a 6% annual payment bond, yield is 8% with a current price of 95. So really all we're going to do is take that formula there and we're going to plug the numbers. So we're going to do this on the basis of a par value of 100. So we get a $6 coupon payment in year 1, 2, and 3. And notice we're discounting it just like we do when we're computing the price of the bond, but we're going to multiply that present value of each coupon payment by the year in which it is received. So we multiply the first one by 1, the second one by 2, and the third one by 3. We're still taking present value. So we're dividing by 1 plus the yield to maturity raised to each of those powers. And then we're going to standardize it or divide it by its current price. So we get a Macaulay duration of 2.82. So I want you to think of that 2.82 as kind of similar to the 6.1 in the example that I gave you before. One important note here, a 0 coupon bond doesn't pay any coupon payments, obviously. Its duration will equal its maturity date. Now, sometimes we want to modify the duration, and so what we do is just divide it by 1 plus the yield to maturity. And I'll show you what that means here in just a second. And then there is another duration called effective duration. And the effective duration is used because not all bonds are simple option-free bonds like we had in that very first example. Some bonds have call features, some bonds have put features, some bonds have convertible features. And so they don't really have a well-defined price response to a change in the yield to maturity. So we need to calculate something called the effective duration. So remember this, effective duration is best used when valuing bonds that have embedded options in them. All right, and that formula is pretty easy. So what we're going to do is just take the present value when interest rates fall. So PV with a little minus sign there, and subtract that from the PV with a little plus sign there. And so note, when interest rates go down, the price goes up. When interest rates go up, the price goes down. So that numerator is going to be positive. and then we divide by 2 times the change in the yield, or the change in the entire curve, times the current price of the bond. That's probably a good formula for you to memorize. And it seems to me like it's very likely you'd be given all that stuff for a problem. Let's go ahead and work through a quick one here. So we've got the new full prices for a callable bond, 99 and 103 respectively. And this is in response to a 30 basis point change in yield, whether it goes up or down. Notice that the current price is 101. So if the yield goes up by 30 basis points, we have either a $2 increase or a $2 fall in the price of the bond. What is its effective duration? And so note, all we're going to do is take the 103 minus the 99 in the numerator, right? I told you that this was going to be a positive number. And then multiply this by 2 times the current price. What was that? 101 times the change in the basis points. So 30 basis points is 0.003. And so here's our effective duration of the bond, 6.6. And note that the cool thing about this one, let me just go back, even though that's on that slide. When you're looking at the question stem, there's really no indication of the maturity date of this bond, and so you don't really need the maturity date, which gives you a sense of the embedded nature of these options. Is that, boy, you could have a 20-year bond and it could be called tomorrow, and so that's really not the maturity date's not really relevant. It depends on the change in interest rates. How about key rate duration? What we've talked about so far is this concept of duration, whether it's effective or Macaulay or modified. And what we're assuming here is that the entire yield curve, remember now we did yield curves in the previous reading, the entire yield curve shifts upward or downward by the same amount. This is called a parallel shift in the yield curve. But suppose that we don't really care about 2 and 3 year yields and 12 and 14 and 18 year yields. We just have a whole bunch of bonds that have that mature in 8 years. And that's what we have. And so we want that key rate duration. In other words, what is going to happen to the price of the bond at that key rate? All right, so notice the definition here. Measures the duration of a security at a specific maturity point along the yield curve. Does not require or consider a parallel shift. It measures the sensitivity at key points. And so there's the formula there. And note that, you ready? This is, oh my gosh, notice that. Oh, that looks almost identical to that. It is, but notice the difference. The difference is that we've got the P minus and P pluses in the numerator. We're taking 2 times the present value times the current price. But here, with the key rate duration, we're multiplying it by 1%. All right, so key rate duration always uses 1% in the denominator. Effective duration, it could be anything. Now, of course, and you should be thinking along these lines, that effective duration is a lot more accurate for lower or smaller changes in basis points. Now, here's a good illustration to give you a sense of the relationship between the maturity date on the bond and its interest rate risk or its duration. And so notice I have a blue line there, which is a 1-year bond, which is almost flat. I mean, it's downward sloping. So when yields go up, that's still bad news. The price of the bond is going to fall. But notice the 30-year bond in red, that has a very steep slope, especially starting at, what does that look like, around 12% and lower. So if you own that 30-year bond and the yield goes up, you're going to lose a lot more in terms of price. So we say that interest rate risk is larger for longer maturity bonds. And so here's the conclusion, that duration is the measure of interest rate risk. So bonds that have longer durations have higher interest rate risks. So just remember steepness of the slope. A long-term bond is going to be really steep. There's going to be large prices when the yield changes. But a short-term bond is going to be really, really flat. Now let's go ahead and expand that conversation to coupons, and this is pretty simple. Bonds with higher coupon rates, let's say 10% versus 5%, are much less sensitive to changes in yields. So interest rate risk is inversely related to the coupon rate. This is an easy LOS. Calculate the duration of a portfolio. This is going to be a weighted average. So look all the way to the bottom. There's the good formula. We're just going to take the weighted average. So we take the weight in one particular one particular bond, and we multiply that by the duration. And so portfolio duration is just a weighted average, just like the beta of the equity portfolio is a weighted average. Now let's go ahead and talk about this price value of a basis point. This is really cool because what we've done so far is we've asked the question, all right, we know that when yields go up, it's bad news for our bonds because the value is going to go down. Now what we know is that depending on the duration of the bond, we can say something like, oh, longer term bonds are going to lose more value. But how about if we ask the question, exactly how much value are we going to lose? And that's what the price value of a basis point does. What it tells us is exactly how many dollars are we going to lose if the yield goes up by, are you ready for this? 1 basis point. All right, so there's a good formula there. It's really just a matter of multiplying. And so let's go ahead and look at an example. We've got 5 million. So for the, and here, this is what I need to tell you. Look at the bottom there. In the US, money duration is commonly called dollar duration. So money duration, dollar duration is going to help us compute this dollar amount. And that's the example that I have here in terms of dollars. So when you're asked to calculate money duration, you have to be given an amount of the portfolio. So there's 5 million. Let's see, coupon is 4.5%. Yield 5.25. There's the price 97.25. Semi-annual basis. Let's see. Total market value, including accrued interest, is 4.98 million. There's Macaulay duration. What is the dollar duration? All right, so we're going to just use that formula there. We're going to take the 2.5 for the Macaulay duration in the numerator. And we're going to, we're going to discount it, right? So we're going to divide by 1 plus the yield on the bond, which was 5.25. And we got to chop that in half because it's semi-annual. And then we're going to multiply that by the price of the bond. So what does that $236.91 tell us? Is that if the yield goes up by 1 basis point on our $5 million portfolio, we're going to lose $236.91. And of course, it works the other way. If the yield goes down by 1 basis point, then we'll gain that. So you get the sense here of all of these durations. What we're trying to do is really just figure out the future. Remember, a client's going to come to us and say, here's a bunch of money. I want to build a swimming pool in my backyard in 6 years. Well, we need to find the right bonds that have the right credit risk, but we also need to find the right bonds that have the right interest rate risk. So we're going to put this portfolio together so that after 6 years, the client says, I want to build a pool for, what were those numbers I had earlier? 14,000 some. You say, here's your 14,000. All of these concepts, durations, all tell us about sensitivity to bond prices to changes in yields. And they're kind of different ways of looking at it, but they really, each of them adds value. So it's not sufficient just to know one thing about duration. You need to know all these duration concepts. All right, how about convexity? Oh my gosh. So what we've been doing so far is we've been talking about duration. And here's the important part. Duration is a first derivative. It is the slope of that price yield relationship. And it is curved. But when you calculate the duration at different parts of the curve, at different yields, the duration is going to be different. That should make perfect sense. But what happens if there's a big old curve in there? We need to take the second derivative, and that's what convexity is. All right, so convexity is just an addition. It's a sophistication. It's a subtlety that helps us more accurately determine the change in the price of the bond. And there's a good formula there for the convexity adjustment and the change in the price the full price of the bond. Now, before you have a heart attack looking at that, it's really, really simple. I mean, all we're going to do, look in the first part there, all we're going to do is take the duration, multiply it by the change in yield. So you're going to have a number like 6.1 times 0.0005, let's say, and then plus, and then the convexity is always going to be in the hundreds. Convexity will be 200 or 400 or some number, and then we square it. We square the change in the yield. So note that for really tiny changes in the yield, when you say the change in the yield of 1 basis point, that's 0.000, lots and lots of zeros with a 1 there, right? You square it, well, you get a really tiny number. But sometimes convexity is really important. So you need to know that formula there because it does say to calculate. And here's a graphical description of what I was saying there. Look at that red line is the tangent line to the green curve, and that's the slope of the line. And so duration only gives you, an estimate. You have to make that convexity adjustment. So notice at the top left and at the bottom right, I have this error in estimating price based only on duration. So you have to add the convexity adjustment. So let me go back here. That's important. Notice that after the parentheses there on the right-hand side of the equal sign, there's a plus. So you're always going to add the convexity adjustment. And this illustration here shows you perfectly why. Now, here's a good formula for calculating approximate convexity. Boy, if I showed you the formula for actual convexity, you would say, I'll probably just guess on that one when it comes to the exam. But here, this is a really good one. And note that it's based on the formulas that we had before. We have two present values in the numerator, so that's going to be like, what was it in our previous one? 103 minus 99. And then we're going to subtract 2 times the current price. And then in the denominator, we still have our current present value, our current price, and then the change in yield squared. Okay? How about term structure? How does this affect the interest rate risk? What is the shape of the term structure of bond yields? Now, we did this in a previous reading, right? Term structures, yield curves can be upward sloping. And in fact, during most economies, yield curves are upward sloping. And let me just remind you that an upward sloping yield curve means that the investors expect the economy, bondholders and investors expect the economy to expand. They expect interest rates to rise. They expect corporations to invest in positive net present value projects, and they expect those positive net present value projects to pay off in lots and lots of cash flows in the future, and then that's going to put some upward pressure on interest rates because everyone's chasing after those positive net present value projects. Now, it can be a different slope. It could be flat. It could be downward sloping. Typically, a downward sloping yield curve is an indication that we're headed towards a recession. It works fairly well in predicting recessions, but not perfectly. But it also depends on government policy. So remember, we talked about fiscal policy, we talked about monetary policy back in our economics days. And so a central bank can either expand or contract by either raising or lowering interest rates. And this is going to have an effect on the slope of the yield curve, which will affect the interest rate risk on the bond because it will affect things like the yield to maturity on the bond and future coupon rates on the bond. And so what do we know? That yield is going to affect duration, and that yield is going to affect convexity. So there's a simple answer to this LOS of describing. Now, this slide swings back to what I did in the second and third slides. Are you ready for this? Describe the relationship between all the stuff that we've done, the duration and its investment horizon. Let's skip to the middle one there. When the investment horizon is equal to the Macaulay duration, the coupon reinvestment risk offsets the market price risk. So let's think about this. Ready? Let's complete the story of what I started in those first slides. All right, over time, if interest rates go up, is this good news or bad news? Well, it is bad news if we want to sell the bond in the future, because as the interest rate goes up, as the yield goes up, bond price goes down. That's not good news, right? But as interest rates go up, we're able to reinvest the coupons at the higher rate. So I want you to think about this. When the investment horizon is equal to the duration of the bond, the good news and the bad news about an interest rate rise or an interest rate fall exactly offsets each other. And you're left with, what was that dollar amount we had? $13.40 or something around there, right? So that's beautiful. Now, let's go up and let's go down above and below that middle part of the slide, and we're going to talk about interest rate risk. When the investment horizon is greater than the Macaulay duration, which is what we had in that first example, then the investor's risk is when interest rates fall. But when the investment horizon, look on the bottom, is less than the Macaulay duration, then we have to worry about rising interest rates. Now, let me go ahead and warn you about what's happening in later readings and level 2 and level 3. In that middle part there, when the investment horizon is equal to the Macaulay duration, when an analyst sets the investment horizon equal to the duration of the bonds in the portfolio, we call that immunizing a bond portfolio. How cool is that? And then let's talk about credit spreads here just quickly as our last slide. Explain how changes in credit spreads and liquidity affect the yield to maturity. All right, so what does this mean? Credit spread is just the difference between, let's say, our bond, the yield on each of the bonds in our portfolio, and maybe some other bonds, or maybe a government bond, or maybe a benchmark bond. So what are the elements inside of that spread? You know, spreads are going to widen for greater credit risk, greater liquidity risk, greater levels of inflation, and greater real interest rates. All right, so remember that right-hand side of the boxes, that's important. When all of those things go up, when the risk goes up and when the rates of inflation and real rates go up, that's going to increase the spread, and that's going to have an effect on the yield to maturity of the bond, which of course will then affect the duration and the convexity. So here's the bottom line here. In our first example, what did we do? We bought a 7-year bond that had a 6-year duration, right? And we immunized that bond portfolio. But what we were assuming there is that the yield curve was going to change in a parallel manner, either up or down. And we know that doesn't happen regularly. So these things in the box over on the right, what they're going to do is they're going to affect that parallel shift in the yield curve. So we need to be careful about in analyzing those things over there on the right. So when the yield curve changes in a non-parallel manner, we may have to sell some bonds. The point here is that you can't just buy the 7-year bond today and wait after 6 years and tell your client, oh, here's enough money to build your swimming pool. If there are, non-parallel shifts in the yield curve or twists in the yield curve, you're going to have to monitor the portfolio over that 6-year period. Boy, that was fun. That takes us through the first 5 readings in this study session. So we have just one more.